Okay, good morning. It's 10:20, so let's start class. I'll give you all of a few more seconds just to log in your answers so I can gauge how comfortable and familiar people are with phase diagrams. Oh, it'll be open for a while. I just want to know where we're starting with because we have a large class. And of course, some of you are in mechanical engineering and you are doing research, and so you may have seen something like this already. Some of you may not. You may have seen on the Carmen module that Chapter 9 has 170 slides, plus or minus 2 slides. There's a lot of animations in there, so it's not as much content as you think. But the way I presented it, I find it helpful if you're looking through the slides that the animations are actually individual slides as opposed to overlaid on top of each other, so that as you're progressing through the phase diagrams, it helps to be very linear about it in terms of your thought process. That is why this slide deck is 172 slides for 3 lectures, maybe 3.5, depending on how well we pace. But I should also mention, and I'll point it out once I put up the PowerPoint slides, but I should mention that the last 30 slides or so are just review. So if you're going through these slides, you feel like, okay, I think I understand it, go to the last 30 slides and just test yourself. There are more practice problems, more lever rule calculations, just more practice problems for you to become familiar with dealing with binary phase diagrams if you haven't seen them. If you've seen them, fabulous, more practice for you, okay? And maybe they're useful systems that you work with. Not always, because some of them are isomorphous binary phase diagrams, so they might not be as relevant. But anyway, so let's take a look. There's almost all, I won't pause it just yet, but I just want to see the responses, just so I can get us started today. Okay, so almost half of you have not seen binary phase diagrams. Okay, so I will alter my pace accordingly. 16%, okay, have seen them but not really familiar how to read them. Some of you have seen them and are vaguely familiar, so this might start the review process for you. And okay, so 11% have seen it somewhere in your homework or in other classes. And 1% of you have actually used it in your research. So I would go find this person because they're most familiar with binary phase diagrams for your study group, okay? Okay, so I'll open it back up in case the other 3 people want to log in their responses. But this gives me a good idea of where we're starting with. And most of the top hat questions today will just be participation because based on this, I sort of anticipated that you won't be so familiar, and it is relatively dense, so I want us to work through some of the problems together without that 20% penalty. So, okay. So there are a few more people logging in. So while we're doing that, a few housekeeping points. You have all received your individual scores yesterday. I wanted to get them out as quickly as possible now that everybody has taken the exams. As I mentioned in my Carmen message to you all, that one of the Chapter 3 questions wasn't deleted properly, so it was counted in your grades even though everybody got 0 because it wasn't supposed to be there. So everybody should see a rise in your in-lecture participation grade, okay? So I've noticed that change in the script. And your TAs are double checking again to make sure your recitation score inputs are correct because the overall script calls in from mastering engineering, top hat in class, and top hat recitation. So, and of course your exam 1 that's come back from testing services. So the script works, but it's not perfect. So bear with us. They're working on it as we speak to make sure that the second version that goes out will be correct so that you don't get different scores in your inbox. Obviously, you can keep track of some of these scores already if you just go into Mastering Engineering or Top Hat, all of that. You can go to the obvious sources already, but Carmen, as is our own scripts, is basically the Hulu of all of this, right? It's a one place for you to go. Canvas takes in, or your Carmen front end interface, takes a very particular format of Excel spreadsheets for it to be uploaded, for scores to be automatically uploaded in mass. So that's why you got the script, because it was just easier for me to write a script and get you all your scores, your exam one scores, sooner rather than later, because I'm trying to be mindful of some deadlines that are coming up for you. I don't think the majority of you are considering dropping the course, but of course it's always useful information to have, especially if there is such a deadline, okay? And if you'd like to speak with me about your grades, in your recitations, your TAs will be handing to you your exam, and also we have all the digitized copies of your Scantron, so if there's any question that maybe something got logged in incorrectly by the Scantron testing service scanner, that is your opportunity to check. And if you'd like to talk more in depth with your TA or me, come to office hours and we'll accommodate that. And I know the drop deadline is the 22nd, so I'm trying to find a time later in the week, in addition to my office hours today, 12 to 1 in Watts 494, so that I'm more available in case people want to discuss that beyond, just the content of the course. Okay, let's see. Did I miss? Oh, and a number of you have told me about homework number 5 not syncing properly to Carmen. We will get on that. I anticipate that that's applicable to everybody, so it's just a syncing problem. It hasn't been an issue up until now, so we'll look into it. My guess is something just wasn't activated properly. Yes, Kevin?
So about the exam?
Yeah.
It's going to be pretty much the same as last night. In class, one answer sheet permitted.
Oh, exam 2, you mean?
Yeah.
Yeah, same mode, yeah. Okay. I believe that's all the housekeeping, unless there's other questions that you have that I haven't addressed. Okay. All right, let's get started then. All right, everybody's logged in, so I'll pause it. About the same. So I would say the majority of you are not really familiar with binary phase diagrams. Okay. That's good to know. Okay, so phase diagram. It is the starting place if you are a material scientist. If somebody asks you, can I make this compound? What do you say to them? Okay, you could do this, which is reasonable and honest, but you could also look it up, and you could look it up in phase diagrams. We will be dealing with binary phase diagrams because that's where we're going to start, but of course you can always mix different components, more than 2 components, and you'll have ternary phase diagrams. You could have quaternary phase diagrams, but then it becomes like a 5th dimensional space, and then who knows what we're dealing with. So today we'll just talk about binary. What happens when you mix 2 components together, okay? And that will be the discussion of chapter 9, which will lead us into chapter 10 on how do we transform from one phase to another to get the mechanical properties that we want, to get the thermal conductivity that we want. How do you get magnetic properties that we want, and so on and so forth, electronic properties that we want. And so on and so forth, right? So this is the chapter I've been alluding to a lot. I kept saying, oh, we'll get to the binary phase diagram. Here it is, we've arrived. So this is the phase diagram. If you talk to a material scientist, they will have committed this to memory, okay? Because it is and has been the binary phase diagram that has dictated it, the industrial revolution and a whole bunch of other structural materials advancement, right? Every single beam that you've driven over, every single beam that's in construction, everything that's anything, anywhere, has started here, right, in terms of building materials. So I highlighted a few terms here. I mean, the back of your chapter has, a very long list. And of course, you could go into depth, but I've highlighted a few phases here. So, and also some terminology that we'll bring up. So ferrite, alpha. Okay, so for this particular binary phase diagram, and I'll also generalize it too. We've said so far when we mix things like nickel and copper or oil and water, right? Those are components. Okay, so here we're mixing two components together, iron and carbon. Okay, so those are two components. So you could see iron is on the bottom here. So this, okay, yeah, so iron here. So this is the composition of carbon. This is what dictates the phase and also the mechanical properties. So how much carbon are you going to put in? And you can please note that it's in weight percent. Sometimes you'll see it in atomic percent. And if you're given a phase diagram like this in some database that you're looking up, this is very generous, right? Because they've converted for you. But if they haven't converted for you, you can go back to the previous chapter where we've talked about conversion from weight percent to atomic percent. Now, sometimes it's easier just to give somebody a weight percent amount. I weigh this out and I mix it in. And this is how I heat treated it. It's much more convenient than, say, add in atomic percent. Of course, when we're talking about stoichiometry, right? When we're talking about nickel carbon, or when we talked about gold copper, we said Au3Cu or Cu3Au. That's the stoichiometry. That's based on atomic percent. So sometimes it's more convenient to talk about it that way. Sometimes it's more convenient just to tell somebody in weight percent. So we interchange, we switch back and forth between these two nomenclatures for that reason. But definitely note what is on your x-axis, right? It could be weight percent, it could be atomic percent. Okay, so components, phase. Alpha is a phase. It is just iron. But we call it ferrite. And its crystal structure is BCC. It's different from another phase called gamma. So this is alpha, this is gamma. So alpha exists right here in this region that's very tiny, but very important. Okay. So that's alpha or ferrite, crystal structure BCC. Then if you increase the temperature, you get to another phase called gamma or austenite. Same name. Its crystal structure is FCC, so it's packed differently, and thus it has different properties. You'll see a demo in this upcoming week where you'll see, ferrite being magnetic and then austenite being non-magnetic. So it has consequences in terms of the magnetic properties. And then on the other side of this phase diagram, you'll see cementite or Fe3C. This is what's called a compound. So what we worked with before when we were dealing with the solid solution of gold and copper, right? We dealt with Au3Cu. So that's gold 3, copper 1. Now it's iron 3, carbon 1. So this is a compound. So you can see here, this is the line. This is cementite. Okay. And in weight percent, you have to put in 6.7 weight percent of carbon. You'll note in the atomic percent, it's at 25, which makes sense. Because if you look at 3 plus 1, subscript here is 1, but we don't write 1, right? 1 divided by a total of 4 is 25%. Okay. So, see, 6.7 might not mean anything to you, but if you look at the stoichiometry down here, that would make more sense to deal with the compound this way, okay? So if I said 6.7%, 6.7 weight percent carbon, I also just told you it's Fe3C. All right. Okay. Now, let's talk about the liquidus. These lines mean something. The liquidus is when you have above this line, so this would be a liquidus. Above this line, you see a single phase region that's just liquid. So if you heat some combination of iron and carbon up high enough in terms of temperature, you're going to melt everything, right? Which we sort of knew. I mean, if you compare it to like just water or any other component that's out there, you heat it up enough, it's going to melt, right? And then it's going to turn into a gaseous phase, right? So this is something that you've seen before already. Then, of course, there's the solidus. So below that, a certain line it's going to be a solid phase. So this would be a solidus right here. Okay. So you can see it's a single component solid phase. So L is always liquid. It's reserved for liquid. There's no special Greek character. Nobody's going to, if somebody's going to use lambda, then they'll use lambda, but nobody will ever use L to represent anything that is, that's a solid phase. Yeah? Sometimes it's dotted because people don't know for sure. So we'll talk about that. That's a great question. We'll talk about that in a little bit. Not all phase diagrams are set in stone or cemented, if you will, right? A lot of these are experimentally driven. They're empirical. Now we have databases where we know the energetic terms, so we can actually calculate it based on Gibbs free energy. And as you recall from previous lecture, Gibbs free energy is just the enthalpy minus T times the entropy, but the enthalpy is just the energy of the overall function of the overall system, E minus, plus PV minus TS. Right? So now we have all these energetic terms where we know, okay, we can actually sort of predict these phase diagrams, and then we can experimentally verify them. But if we're not sure, we just draw a dashed line and we say, okay, we think based on some smattering of data points and some calculations that it's going to look like this. And you actually see that a lot at high enough temperatures. Sometimes we just don't have reliable readings, or not enough people have worked on them to collect that sort of data. Both phases. Yeah, so we'll go into that and really drive home the difference between a component and a phase. Absolutely. So a component is when you add iron, that's component one, and the other one is on the other x-axis, right? I'm sorry, the other end of the axis. So you start with iron. If you don't add in any carbon, then it's at 0. You start adding in your second component. Here in this phase diagram, it's carbon. Okay. Then we'll talk about a really special point, which is the eutectic. This is important in iron-carbon phase diagrams, but it's also really important in any sort of binary phase diagrams, because if two things can mix together, their melting temperature will actually be depressed, which means it gets lowered. This is great news, because now you can operate at a lower temperature. You don't have to increase the temperature as much to melt. So here you see this is the eutectic temperature, right? It's about somewhere between 1100 and 1200. Sorry, it's 1147 degrees Celsius. Okay, so we'll talk a lot about this eutectic, about the composition, where it is in the diagram, what the reaction is. So you can see here it's going from solid. If you just drop down, the way one would be systematic about any phase diagram is just to start at a really high temperature where you have liquid and just work your way down and see what you hit. And that way you ensure that you'll hit all the phases you're supposed to hit, okay? So if you just go down, you could see, okay, so it starts as liquid. It's going to end up with two phases, gamma and cementite. Okay, and so it's written on there already. Eutectic temperature, where does this point occur? Well, you just go over to the y-axis. Here it's already noted for you, 1,147 C. Okay, and we'll see these terms again and again and again when we talk about binary phase diagrams. Another important point about iron-carbon is the eutectoid. So it's eutectic-like, but instead of coming down from a liquid state, let's say you have this solid gamma phase, and you come down right at this composition of 0.76 weight percent carbon, that's denoted here. If you come down, you can see it gets split into, it gets split into alpha and iron carbon, iron carbide or cementite. What is the ideal state of this compound? Whatever you want it to be, because when you look at a binary phase diagram or any phase diagram, it's in equilibrium. What the phase diagram is trying to tell you is at a certain composition and a certain temperature, this is the thermodynamically stable state or thermodynamically state in equilibrium. This will exist if you go to this composition and this temperature. So it depends on where you are. If you're at 1600 C, it doesn't really matter how much carbon you add in this range with the blue arrow I just drew, you're going to be in a liquid state. If you're somewhere here at 500 C, say, so if you're at this dot right here, you're going to have two phases. So it depends on where you are. Treat it like a map. Go X, go Y, and it'll tell you where you are in life, okay? So eutectoid, now you're going from solid to two phases, okay? Hypereutectic, so if you're in a region, in a compositional region that's higher than the eutectic composition, so then you could also anticipate what's about to happen next. Hypoeutectic, so this region, okay? So then, of course, you can also have hypereutectoid, hypoeutectoid. It just denotes, it tells people, you know, which region you're in. By just saying that definition or that terminology, you will have known, oh, okay, this is what the microstructure looks like. This is how the material is going to behave mechanically. Okay. Peritectic, also important. So when you have a solid here, liquid and solid, and then you see it going to gamma. So let me change color. So here you have a liquid state and some delta phase. So some liquid phase and another solid phase called delta. By the way, delta is also BCC. So this material goes from BCC to FCC back to BCC if you just increase the temperature, okay? So if you happen to be here and you drop right down at this composition, it's called a peritectic change. We'll go into this. I'm just throwing a whole bunch of words at you right now just to navigate and see where all these things are on a binary phase diagram, okay? Okay, tie line, we'll talk about that. So if you're at a certain composition and you want to know, okay, how much of this gamma do I have versus how much of the cementite do I have? So you draw a tie line, and we'll go through some examples on how to do that. And then from the tie line, you can calculate phase weight fraction or phase weight percent based on the lever rule. So we'll talk about that. And to answer Kevin's question, what is the preferred state? It's the equilibrium state depending on your composition, your pressure, your temperature. Clearly, pressure is not on this diagram, and thus the assumption is that we're working at 1 atmosphere, which is just on Earth. Okay? If a system is pressurized, the phase diagram will note that. And there are a lot of people, particularly in Washington State, because there's a large national lab there, where people study what happens when we pressurize a system to basically mimic that of the pressure one would experience in the Earth's core, to understand, you know, where we came from and all of that. So in those types of cases, those phase diagrams don't note what the pressure is. For this class, obviously, you know, we'll work at just 1 atmosphere. Burning question from Kevin, yes?
So I understand the austenite is a solid, but are there any other solids present in the phases? Or?
Anytime you see a Greek letter or a compound like this, so alpha, gamma, delta, and here is cementite, which is Fe3C. That's a solid. So anything that's not an L is a solid. Okay? Okay. So what I would do is, if you're reviewing, pull this slide up again and see if you can just go through these terms. These terms are also all in the back of the chapter, right at the end of the chapter. So if you go through and you can say, can I locate this? Do I know what this means on this phase diagram? Then you're set. And that's also where your learning objectives on chapter 9 come from as well, okay? These are the starting terms. The back of the end of the chapter has many more terms, but I didn't want to overload you with the beginning. Okay, so composition temperature, equilibrium, structure, right? The questions all lead to this, which is if I have some component A and I have some component B, we talked about solid solutions, we talked about Hume-Rotherhey rules, right? If they can make a solid solution, what phase should I get? How are these atoms going to pack? So if you add aluminum and copper, okay, great. Well, they can be sort of disordered like this. You can already sort of see some grain boundary situation happening here. Okay, fine. They can pack like that. They can also be really ordered, as you could see here. They can pack somewhat alternatingly like this. So how do we know what we have? Like, how can we predict this is really the basis for chapter 9. Okay. Back to Zach's question, component versus phase versus composition. So component, I'm adding A and B. That is component. That's two components. If you add A and B and C, so nickel, copper, gold, those are three components that you just added in. Okay? If you add nickel and copper, that's two components. But they can make different phases. So we'll talk about isomorphous binary phase diagrams, or if both systems, like nickel's FCC and copper's FCC, when you mix them together, based on the Hume-Rotherhey rules, you would expect that you would just get FCC. You wouldn't really expect some magical transformation to happen unless you induced it. Okay, so you would just expect I would get FCC phase out of this. I would get some solid solution, and the phase would be FCC. Okay. Composition. I have to tell you, I added in 50% nickel, 50% copper. That's your composition, right? So you would write NiCu. They're 1-to-1. The gold-copper system, right, the composition there is different because you can have this composition. You can also have this composition where it's 1-to-4, but here is, or 3-to-1, 25% overall, but here's 3 gold to 1 copper, or 3 copper to 1 gold. Okay, that's the composition. And then the phase that we were talking about previously, if you heat it up to a certain temperature, it'll go into a disordered state. But if you cool it down, it'll settle in and form some ordered phase. Okay, so even though you're at one composition, depending on how you vary the temperature, you can get different phases. And that's what we've seen with iron. That's what we know with water, right? H2O will always be H2O. The composition will always be 2 hydrogen to 1 oxygen, right? And if you change the temperature, right, you'll get ice or water or steam, right? So that's what we want to know. What phase are we going to get? But there, you're just changing the temperature. You're not really changing the composition. The binary phase diagram you just saw changes the composition, right? We're changing the amount of carbon we're adding in. So to be more specific about Zach's point, single component. Here in this system, we actually treat H2O not as 2 components. Now, if you talk with a chemist, I think they would argue and say, well, you have hydrogen and oxygen. Wouldn't that be 2 components? When you're having conversation with them in that jargon, absolutely. In this case, we treat it as 1 species because we're not changing the stoichiometry of H2O. So we're treating H2O as 1 component. Okay, so that's the distinction between the chemical nomenclature and material science for this particular example. So as I mentioned, we can talk about different phases as well. So things can be in the liquid phase, things can be in the solid phase. Now, when iron's in solid phase, we've seen, okay, it could be alpha, it could be gamma, it could be delta. All right, so then we have to start naming the different solid phases because we can't just say, oh, it's solid iron anymore, because the atoms will pack differently, and thus you have different solid phases. Of course, then you could think, well, obviously there's solid to solid phase transformation. So unlike water, right, when you go from solid, you increase the temperature, you go to a liquid. We just saw an example of how you can go from a solid to another solid to another solid, and then liquid. Okay, so these are the types of phase diagrams that we'll be talking about, where you can have solid-solid phase transformation. And there's a lot of cool things that happen in the solid phase when you go from solid to solid phase transformation. There's a lot of cool optical properties, electronic properties, switching properties for smart materials. They happen to be called thermochromic materials. That means Their optical properties change just by changing the temperature in the solid phase. So you're not even going solid liquid, okay? Okay, now components. We can treat, okay, if we're treating H2O as one component, then we could think about, systems where it's useful to us. So salt, NaCl, can be another component. And this is particularly useful for a morning like today when the snow is coming down on the road, right? There's a reason why people salt the roads. It brings down the eutectic temperature. Your brine stays brine at a lower temperature, and we'll see a phase diagram of that. And then there are examples that you've seen already, nickel, copper, right? That's two components. You can throw in any other two elements, lead, tin, magnesium, lead, bismuth, tin, all that. I list those examples because, one, their binary phase diagrams aren't too complicated, so we can deal with them. And also, they're industrially relevant, right? When you solder these days, you don't really use lead solders anymore for health reasons. They're bismuth-based, and so people figured out how to combine two other elements so that you can solder at a lower temperature and much more safely than using lead. Okay. I threw this in there just to remind you of what you're already familiar and comfortable with, which is water. All right, so if you track at your component at a particular atomic percent, so if you draw this table and just go systematically through it, you will not miss a phase, okay? So obviously, if you have 100% H2O, for your temperature, pressure plot at 1 atmosphere, right? All this information has to be given so that you know you're working under the same conditions as somebody else. If you drop the temperature, right, 110, 90, and then down to 0, right? So here, you could see that you're at 110, you're in the gaseous phase. At 90, right, you're in the liquid phase. 0, you're in the solid phase. Right, pretty standard. Composition, well, it's a single component, so you're just going to have 100 weight percent of something. Just like the iron example. If you don't have any carbon yet, you have 100 weight percent of just iron, okay? This is pretty simplified because it should just be, right? It's just a very systematic approach. So then you can also calculate phase weight fraction. Well, you don't have any other component, so your fraction is going to be 1, okay? So very standard. This is something you've already seen. You may have seen it, more like this, because I think in your chemistry textbooks they usually plot pressure as the y-axis and temperature as the x-axis. So you probably have seen something that looks like this, okay? Where low temperature and low pressure, you'll have solid, and then you increase temperature, you'll have liquid, and then you increase pressure as well, you should have gas. Actually, I think this is low temperature, high pressure. Yeah, so it should be, sorry, I think it should be flip of that. Oops, oh, my chicken scratch. Okay, so this is obviously very helpful for when you're reading the back of, some frozen dinner or boiling water. This is probably the example you've heard before, where if you're at a high pressure city versus a lower pressure city, right? Denver versus LA, or something like that, or somewhere in the Tetons, where you're at lower pressure versus if you're in Death Valley, right? That matters on how you boil water. Okay, so we can do the same for iron. Okay, so if you look at temperature versus pressure, so temperature is the y-axis, pressure is the x-axis. You can see if we keep at 1 atmosphere and we just increase the temperature, we go through exactly what we just saw in the binary phase diagram. You see it going from alpha ferrite, so BCC, to gamma austenite, FCC, and then it goes back to this delta BCC crystal structure, and it's just all solid. All right, and then above gamma, of course, is liquid. So if you go to a high enough temperature, sure. If you go above 1538 degrees C, sure, you'll melt your iron. But you will have gone through 2 solid-solid phase transformations, okay? And then if you reduce the pressure enough and you increase the temperature, you'll have gaseous iron. It can happen. not at any reasonable lab scale, I can tell you that. But it can happen, and people do study these things. Okay, so once again, you can go through, and as I've said, start at the top, 1540. So I chose a temperature that's right above the melting point of iron. So where you have liquid, and then you drop the temperature to 1395, so you could see it's like right there. So now you're going to get solid, although I think this should be 4. And then you drop it to 920, so you're 920C, you're somewhere here. You're in gamma phase, so gamma iron, and then in solid phase you have, and then at 900, which is below the solid-solid phase transformation of gamma to alpha, you now have alpha. And so basically I'm just reading off the chart. Okay. Okay. What information can you get from a phase diagram? It's in the name. You can get the phase. And you can get the phase weight fraction if you know your composition. Okay? But most importantly, it is the thermodynamic equilibrium of your material. Okay? So that means then, one moment, let me switch over to Top Hat. So that means then, what can we say about a phase diagram that is true? Is it that the phases shown on the diagram correspond to the lowest free energy of the system for the indicated temperature and compositional values? Is it that metastable phases cannot be found on phase diagrams? Is it that it is not possible to transform one solid phase into 2 other solid phases upon cooling? Or is it that a given phase shown on a phase diagram has one and only one discrete composition? You can talk to your neighbor, you can discuss it amongst yourself, you can think about it internally. While you do that, I will switch over. I think I made a mistake on this. Oh yeah, this should be. Let me see, this should be liquid, solid, gas. Let's go back. And there could be multiple responses that are true, by the way. Okay, so we're just about there. Let's get your answers in, the last 2 people, and we'll discuss. Okay, so it looks like we're at 100%. So let's see. Okay, great. Well, we covered, absolutely. only 3% said that metastable stable phases cannot be found on the phase diagram. So I just mentioned that only thermodynamically stable or thermodynamically states of something that's in thermodynamic equilibrium. That means it's a stable phase. It's a thermodynamically stable phase can be found. If it's metastable, it can't be found. So what we've worked with before, that's a metastable phase that can exist, but you won't find it on phase diagram, is a whole bunch of metals put together. Alloy, yes, but it's a very particular alloy. Metallic glass, right? That's a metastable phase. Like we talked about quenching a bunch of metals put together, and then it just arrests this glassy state, right? That's a metastable phase. Yeah, so this should be true. Let me turn it on. Yeah. Metastable phases cannot be found. It has to be a thermodynamically stable phase for it to show up on a phase diagram. Okay? So metastable phases can exist. They won't be on your phase diagram. That's the difference. And then, yeah, well, you guys got the rest, so I won't belabor the point. But yeah, you guys understand that something that's energetically stable and lowest, will show up on the phase diagram, right? Okay. Okay, so let's go back. All right, so we've talked about that. So many things. What we'll talk about, what you can extract from a phase diagram, you can extract the equilibrium composition of each phase. You can look to see what is the solubility limit for each phase. The temperature of solidification, we talked about when a material goes from liquid to solid, you'll know when that will occur. And then the microstructure, which is extremely important for when you're actually trying to engineer something. Okay. And so we'll talk about perlite. That's a pretty prominent microstructure. You'll get to know and love it by the time we end chapter 10. Okay, pretty useful phase diagram, something that you're familiar with. You add salt to water, you get a brine. A brine is a solution of salt in water. Okay, so if you look at this phase diagram, one component is just pure water, right? Okay, great, that's expected. If you don't have any salts, then of course, right, there should be a transition right here at 0C. Okay, so that's just going from water to ice, 0C. Now, if you start adding in some salt, 10 weight percent, 20 weight percent, 30 weight percent, all the way up until you don't have water anymore and you just have 100%, let's say you don't have water, right? You have 100 weight percent salt, then salt behaves like salt. NaCl, so then you could look at this line over here and see. So then if you're anywhere in between, you can know, okay, if I'm 10 weight percent sodium chloride in 90 weight percent water, then if I'm at negative 30C, you're going to have some ice and some NaCl that's coordinated to H2O. If you increase the temperature, you're going to have ice and then some brine. So that's just salt water. Okay? Brine is just salt water. And then if you just increase the temperature some more, then you have just brine. So that's just your salt in water. So if you increase it to 10C, now you're a little bit warmer. If you increase to 40C, now you're a little bit warmer. It's not until you hit 100C, that's when your water will start evaporating. Right? So what's important here is this eutectic point, okay, that I've drawn. So that eutectic point is important because you see the depressed melting temperature. It goes from water to brine, right, going into ice. So if you are at 20 weight percent of salt in water, or in H2O, I should say, because water is obviously a phase. If you have 20 weight percent of NaCl in H2O, you've decreased that melting point to negative 20 C. And that's exactly why you salt your roads. Okay? So you prevent ice formation, or at least you push it off until a lower temperature. Yeah, so that's a solid form. It's just NaCl coordinated to, so ice would be solid, and then, so brine is the solution, the liquid form. And then NaCl coordinated to 2 moles of H2O is in the solid form. Yeah. So whenever you buy like chemicals, I don't know if you've ever ordered like from Fisher. Okay, probably have not. But anyway, when you buy chemicals, they'll say, especially if it can be dissolved in water, it's already actually hydrated sometimes because of atmosphere. And so the hygroscopic materials will already be coordinated to H2O. It's already in the powder that you dump out. So they'll say like NaCl, well, something else, potassium permanganate or what have you, and they'll say dot X something, you know, H2O. That means it's already coordinated to that, even though it's in the solid form. Okay, so review of Gen Chem right there. Okay, so salt, water, pretty useful for your life, especially on a day like today. You change temperature, so you can go from A to B. You go from brine and NaCl to now just brine, so you're changing phases by increasing temperature from A to B. If you stay at the same temperature, here, I picked a point 30 degrees Celsius. You go from B over to D. You've changed the composition, right? Here you've gone from 30, now you're at 40 weight percent. Same temperature, but you've changed the composition. You've also changed the phases that you have, okay? Okay, so that was that. Okay, so now things are starting to get just a little bit more complicated. As I've said, you know, you can look at different temperatures. So 10C, you have ice and brine. That's here at 30 weight percent. So should actually be here. So sorry, I looked at the wrong composition. So if you're at 30 weight percent, which is denoted here, and 70 weight percent water at 1 atmosphere, if you're at 10, oh, I'm sorry. Oh. Sorry, you're at 10C, then you can read it off as brine and NaCl. 30, we've just covered that. Okay, let me skip ahead because for the sake of time, we'll pick up with Gibbs phase rule, but I want to introduce it so it sort of simmers over the next few days for you. Okay, when we talk about where am I in the world, what does my material want to be, you also have to consider if you change from that one dot, how is it going to change your system? So we have Gibbs phase rule that will tell us how the system will change by telling us how many degrees of freedom do we have. So I'm just going to go back to, we haven't gotten there yet. Let me go back to an example that you know well. Okay, let's go back to your water example, your H2O example. If you're on this spot right here, let me pick red this time. If you're on that spot, right? If you change temperature, let's say you change this way, okay? Well, you went from being both in the gas phase and the liquid phase to just gas now. So you changed the number of phases. So if you want to get back on this line, let's just say, you don't have a lot of degrees of freedom because if you change this way, you have now to change your composition to get back on that line, okay? If, let's say, your H2O right here, if you change pressure, it doesn't really matter. If you change your temperature up until a certain point, also doesn't really matter. You're just in that one phase for this entire region. If you're on these lines, if you're on these phase transition lines, though, you're limited by the number of degrees of freedom that you have. Because as soon as you change one thing, you got to change something else back to get back onto that line. And so that's what Gibbs phase rule tells you. It relates the degrees of freedom that you have, like how many non-compositional things you can change about a system, to achieve a certain number of phases. So let me just go back to that quickly to drive the point home. So F is related, the degrees of freedom is related to the number of components that you have, C. So if you have nickel copper, that's 2 components, okay? P is the number of phases. So we'll talk, in binary phase diagrams where we see, okay, we can have 2 phases. And here, actually, sometimes in certain books, like the other popular material science book is written by a person named Callister, they generalize it to N, which is the number of non-compositional variables. So are you changing pressure? Are you changing temperature? What are you changing? So they generalize it to N. And that's your number. Here in your Shackelford book, they say 1, because they already assume that you're working at 1 atmosphere and you're only changing temperature. That's where this 1 comes from. So if you're thinking about changing pressure and temperature, Shackelford already says, let's just always operate at 1 atmosphere, and thus you only have 1 non-compositional variable that you're going to change, and that's your temperature. So that's why the 1 is there, okay? And so your book goes into detail as to why that is. So then you can look at a phase diagram, you could say, okay, what is the F? What is the number of degrees of freedom that I have? If I want to keep P the same or C the same, you can relate it all, okay? So we'll go over an example together for the next lecture, but I want to leave you at this so that, you've seen it, and then we'll start on it next time.